All right, Seth, please.
Thank you for the introduction, and thanks for inviting me for this seminar. I think this is great for the community. So today I wanted to give a talk on some work I've been doing for the last few years now on how to use scale and tune sequential Monte Carlo samplers, and more generally annealing algorithms more broadly. So the motivation of every Monte Carlo talk is we have some complicated probability distribution. We're going to call it pi1, and we're going to assume that we are in the sampling context where we can evaluate it up to a normalizing constant. So gamma we can evaluate, z we can't. I don't think I need to motivate this too deeply for this audience, but yeah, this is a very common scenario in Bayesian inference, statistical mechanics, graphical models, the applications kind of go on. But the general goal that we have is we want to draw inferences, which we can formalize by saying we want to compute expectations, and we want to maybe be able to evaluate normalizing constants. In general, this is hard. So I'm gonna demonstrate two naive ways of computing normalizing constant and expectations. The first thing for normalizing constants, we can do this actually fairly easily by introducing a reference distribution. So a distribution where I know how to evaluate the density, a normalized density, and I can officially generate samples. Then we can do some algebraic tricks where we can write the normalizing constant and we can multiply and divide by the reference density. So we can write the normalized constant as an expectation with respect to the reference of the unnormalized likelihood ratio G. If we can use our samples from our reference, we can basically create an unbiased estimator for the normalizing constant, which is unbiased and it gets the job done. And if you take n to be large enough, you're going to get a consistent estimate. However, the problem that we have here is that the variance of this normalizing constant estimator is going to be really bad. In particular, you can show that the variance of the normalizing constant estimator is controlled by how far away the reference is from the target. In particular, it's equal to the chi-squared divergence divided by n, which there's ways of showing that this is upper bounded. This is lower bounded by effectively the exponential of the KL. So when the reference is bad, which is going to be most of the time, this basically becomes completely unusable. So that's one solution that did not work. Now, for expectations, we have a similar problem, or another naive thing that we can do is we can just run an MCMC algorithm. So I can, again, initialize from my reference. I can generate a sequence of a trajectory from some Markov chain M that targets our target distribution. And if we average out across the trajectory, you get an estimate of the expectation of whatever function you want. In practice, as we all know, this kind of sucks in practice, naively, right? So MCMC works really well for understanding the local structure of a mode, but it has really hard time traversing between modes. So multimodality is a fundamental problem that occurs in modern statistical inference problems so you end up having that these MCMC chains, if you just run them naively, they get trapped in local regions of high probability, and they basically lead to poor mixing. And in practice, we don't know how bad this is going to be because we just run these trajectories, and it can trick us into believing that we've converged, but in reality, we've missed a huge chunk of our distribution. In our practice, we also don't know where these different regions are. So if we miss them, we're completely out of luck. We're kind of blind. So one way to actually tackle both of these problems is by actually combining the two together. So this is the first iterate of what I want to be talking about, which is a baby case of sequential Monte Carlo samplers. So what we're going to do is we're going to go back to our reference, generate a bunch of particles from the reference, and then we're going to use our MCMC chain to propagate them all forward. So they're going to land in some of the nooks and crannies, depending on each of the particles is going to find its own separate mode. And then we can reweight the particles proportional to how likely they were at the reference. So this is just using importance sampling again. And then we can optionally do a resampling procedure where we can take these non-uniform weights and basically bring them back to uniform, which corresponds to effectively killing off some of the lower weights and repopulating the higher weights. And if you pick n to be large enough, this will actually converge to, it will give us a particle approximation of our reference and a particle approximation of our target, which we can plug into the same formulas that we had earlier, and we get expectations and normalizing constants. In practice, for the purpose of this talk, I'm not going to be focusing on the details of the resampling procedure. In practice, there's a phenomenal work done by Nicolas Chopin, Sumit Singh, and co-authors. My recommendation is just to use SSP or sorted systematic or any stable resampling procedure that in that paper. So the issue with these methods, though, is this works really well, actually, when the reference, again, is close to the target. So if the target is like a small perturbation away from the reference, this is actually going to be quite stable and robust. And you're going to get a healthy particle diversity after everything's said and done. But the problem becomes, again, when the reference is far away from the target, and in particular, when the reference shares very little overlap, what you're going to find is some particle degeneracy occurs. So the weights are effectively going to be all dominated towards one particle, and then everything else is going to be relatively zero. And when you do this resampling procedure, most of those particles are going to be dead. So even though we have a bunch of particles, effectively, we may only have one. And so essentially, we have stability when the reference is close to the target, and we have fragileness when things are far away. So a simple solution, and this is kind of motivating what we're going to be talking about for the next 50 minutes, is instead of doing a direct inference, going directly from the reference to the target, we can introduce a sequence of distributions in between where each of the distributions is sufficiently close to each other where this procedure that I described earlier is robust. So if we concatenate these procedures, we basically propagate the inferences from the reference incrementally over time, we can hopefully get from the reference to the target in a stable and efficient way. So this idea that I'm describing is what is sometimes called annealing. So for notational purposes, I'm going to always be referring to pi1 as a target distribution. In the back of your head, think of a posterior or something complicated. Pi1 will always be the reference. Think of something like the prior or Gaussian or something that you can, again, simple and easy tractable. Pi beta is going to be some continuous interpolation from the reference and target. This could be anything. In particular, a common case is what I call the linear path, which linearly interpolates between the log densities of the reference and target. So you can already kind of see why this works. So effectively, annealing introduces an extra dimension to our problem. So we can take our complicated d-dimensional space that we're in, and we're effectively turning our inference problem into a d plus one dimensional problem, where annealing essentially acts as a way of building a bridge between the different modes through the reference. So like in this y-axis over here, you have beta represents our annealing parameter. So at the top, you have our target, which is bimodal. At beta equals 0, you have a reference, which is unimodal. And essentially, you can see that the annealing path essentially gives us a way of finding all of the different modes if we start off at the reference. In practice, we can't do a continuous interpolation because we have to implement things. So we have to discretize. So I'm going to just presume for now that we have some discretization of our annealing schedule, which partitions the unit interval, where beta equals 0 is always, beta 0 is always going to be 0, and beta capital T is always going to be 1. And we're going to have some sequence of interpolating distributions in between. So going back to so now we have all the ingredients to actually describe SMC samplers. So we're going to be repeating the same procedure, but just I'm going to be iterating now. So again, the algorithm corresponds to generating n particles that are maybe uniform weight. And then we're going to propagate them all forward using, sorry, 1 second. We're going to be propagating them all forward using our MCMC algorithm. So we're going to now presume that we have an MCMC algorithm targeting the Tth annealing distribution. And then we're going to reweight according to some procedure. A classical case that I'm going to be using as the foundation of this talk is we're just going to be weighting according to the likelihood ratio from one distribution to the next, but there are more complicated ways of doing this. And then we can maybe optionally do a resampling procedure. So given a particle approximation of the reference, this now gives me a particle approximation of the first annealing distribution, then I can iterate that over and over again to get a particle approximation of the Tth annealing distribution. So if I simulate this forward, I now get a particle approximation of my entire path, not just the reference and target. So this resampling procedure itself, this is an optional thing. So there are a lot of dials that you can kind of like move around and get different algorithms. This is a framework more than a specific algorithm. So in particular, there have been a lot of different variants. The one that I just described is sometimes called sequential importance resampling. This corresponds to doing a resampling procedure at every iteration. In this case, you can kind of think of it as like the number of resampling time. So here we're going to denote T0 is always going to be 0. I'm going to say T sub R is always going to be T. And then the T1, T2, all the way up to TR are going to correspond to the resampling times. So R represents the number of resampling intervals. So if I don't do resampling at all, I'm going to get R equals 1. If I do R resampling every iteration, R is going to be equal to T. Adaptive resampling is a more common thing to do. So this is where I don't necessarily want to make my particles interact every iteration. I may only want to trigger a resampling event whenever the variances of the weights get too high. So this is sometimes called adaptive resampling. I'm not going to specify the formula for ESS, but this is a very common thing. So you can get that from the weights. So in the adaptive resampling case, the number of resampling events is actually random, but it's somewhere between 1 and T. Third special case, this is actually quite also important. This was first proposed by Bradford Neal, is called annealed importance sampling, which corresponds to doing no resampling whatsoever. So this is a special case of sequential Monte Carlo samplers. In this case, R is equal to 1. And this has the other advantage where no particles need to interact with each other. So you can do this fully distributed. So I've now hopefully described like an algorithm. So sequential Monte Carlo samplers has been around for the last 20-ish years. And it's kind of been the gold standard for Bayesian inference especially. It's been cited thousands of times. It's been applied in pretty much every single area of computational science and modern machine learning. And again, it's a framework that allows a lot of flexibility. There are many different ways of doing this reweighting procedure. There's many different ways of doing resampling, and all kind of like fit within like these string diagrams that I showed earlier. And in particular, this is very relevant for modern machine learning, and where you can also incorporate using sequential Monte Carlo samplers to incorporate flexibility into our sampling pipeline while still preserving the accuracy and correctness that we desire. So in particular, you can use this to incorporate flows, diffusions, transports, et cetera, et cetera. So all of the work that I'm going to be talking about today actually applies in all of these different scenarios, but for the purpose of just pedagogy, I'm going to be focusing on the classical case where you're just reweighting according to the likelihood ratio. So there are a couple things here that make SMC samplers not the most friendly algorithm to work with. In particular, I described a lot of moving parts, and if you mess up any of them, it completely falls apart. So for example, how do I actually pick these annealing distributions? That's fundamentally important. There's a lot of different design choices that we have here. How do I pick the number of particles? How do I tune the annealing schedule itself? Like the choice of the schedule matters a lot. How do I trigger resampling? When do I do it? Does one resampling strategy better than the other? So that's all based around tuning. Another problem is some problems are just hard, and sometimes you did a bad job implementing. So we want to be able to identify when a problem that we have is actually hard, and what can we do about it when that is the case? And also, if we do a bad job implementing, can we see that in the algorithm itself, and can we correct it? Another more meta question is, why bother doing this annealing at all? Right, so like there are competing resources that are happening. So by adding in these additional distributions, I'm using my resources that I could have been just using to simulate more particles, and just maybe running importance sampling without all this like fancy annealing stuff in between, and just run it for much, much longer, and maybe generate much, much more particles. So we want to go back. I'll talk a little bit later today why annealing itself is actually fundamental. Going directly from the reference and target is actually it's fundamentally different than targeting a path itself. And if there's time, I want to spend a bit of time also talking about why use SMC samplers when instead of other algorithmic frameworks. So for example, like what I described here is a particle-based method that is built around the sequential Monte Carlo framework. But there are competing algorithms, say in Markov chain Monte Carlo, that also use annealing, that also use all of these different, that incorporate the same amount of flexibility, but they use the resources in a different way. So, and turns out they also kind of perform kind of comparably. So like there's a particular algorithm that I want to talk about parallel tempering later on that I'll show. I want to answer the question, when should you use one versus the other? So that's the preamble for the talks. And now we're going to go into new things, I guess. So before actually like doing the analysis of SMC samplers and tuning, I want to just like lock in what is the computational framework that we're going to be operating in. So we're going to be assuming that there are n particles, and each particle can evolve independently of each other. So this is kind of acts as like a parallel cost. Like these are the number of parallel particles that we're simulating. The number of annealing distributions, each annealing distribution acts as a sequential cost, right? So like you have to simulate one distribution at a time. So the number of annealing distributions that we have actually directly correlates to the runtime of our algorithm. And again, we're going to be assuming that we have some fixed schedule for now, but we're going to talk about later how to pick that. And then finally, the resampling intervals are, this corresponds to how often that our particles have to interact. So this is in some sense like a communication cost. So whenever you have to do a trigger resampling event, you're basically forcing all the particles to like interact with each other. And this forces them to share memory and actually like work together rather than just fully independently. So in all of these design choices that we have, so any resampling strategy, any set of number of particles, any number of annealing distributions, any resampling strategy, we're all going to give us a valid SMC sampler. And so we want to be able to analyze like how do these different design choices impact the performance of SMC samplers itself. So one way to do that is by looking at the normalising constant estimator. I'm not going to go into the details of how this thing comes about, but essentially you can look at the average of this incremental weights. So these G and T, remember this corresponds to the incremental change of weight from one that each particle has to go through at, so G and T corresponds to the nth particle's change in weight from iteration T. So if I average that out across the different resampling intervals, this will give us an unbiased estimator. So what we can analyze the performance of this algorithm for the different design choices based off of how it impacts the variance of this normalizing constant estimator. In practice, this is quite hard, right? Because the specific mechanisms of the MCMC move that causes temporal correlations. The resampling moves themselves force the particles to interact, so that causes spatial interactions. And so if you want to just directly compute the variance of this is very hard. And in practice, this is intractable without making some strong assumptions. So we're going to make some strong assumptions. I'm going to make my life easy and pretend that we are living in this spherical cow model of SMC samplers. We're going to pretend that all these different interactions don't exist. So this is in some sense like an equilibrium assumption. And this is a very strong assumption that does not hold in practice, but this will give us some insights into like what are the actual design choices, like how these different schedules actually like matter. So our analysis does not allow us to like disentangle the specifics of the resampling strategies or the MCMC moves, but this zoomed out view does give us some meaningful insights regardless. So in particular, you can show that under the assumption that all these incremental weights and these complex interactions don't exist, there exists the relative variance of the normalizing constant estimator satisfies this equation. So there's 3 letters that are worth like looking at here. N, remember, is the number of particles. There exists some number d of t, which I'll talk about later on what that is. But this is in some sense like the total discrepancy from the reference and target. Then this only depends on the annealing distributions. And then rho is in some sense like it's a number that lies between, it's a deterministic number that lies between 1 and t, which in some sense accounts for the effective resample size. So resampling, right? Like I can trigger resampling events quite often, but I may not be gaining the value of triggering a lot of resampling events if I'm resampling them at bad times. So regardless of the resampling strategy, regardless of the times that are actually being triggered, you can ask what is the effective number of resampling moves that like an optimal, if I trigger them at optimal times, what is the rough number of resampling events that are actually happening? So this rho depends on the codes like the efficiency of the resampling strategy itself. So we're going to talk a bit more about how to analyze this in a bit, but I want to just make a note that even though that we are doing this simplified regime, the actual design choices that come about are extremely robust to these assumptions, and the tuning actually works without making these assumptions at all. So given this SMC sampler, right? So we can now take limits in different regimes and see how the impact of the number of particles, the resampling strategy, as well as the annealing distributions actually impact the variance of the normalizing constant estimator. So let's first look at the case of the number of particles. So let's fix the number of distributions. Let's fix the resampling, the effective resample size rho. So you can see that if I have 1 particle, so if I like take the limit as n goes to 1, so this, first of all, this variance is going to be monotonically decreasing with the number of particles. So the maximum variance you're going to have is when you just have 1 particle. It's not going to be very good, and you're going to get this exponential dependency in this discrepancy. You can also take the other limit as the number of particles goes to infinity. And in this case, you will get the variance will go to 0, but the rate at which it's going to go to 0 is going to still have this exponential dependency in this discrepancy. So if D is quite large, you're kind of out of luck. Another thing that we can look at is the effective resample size. So you can show that the variance is actually monotonically decreasing with rho. So as I increase the number of resampling moves, as I make my particles interact more and more, I will be seeing advantages. So if I don't resample at all, so this corresponds to annealed importance sampling, then you have that the variance is going to be approximately exponential of the discrepancy divided by n. So you still have this exponential dependency on the number of resampling in terms of the discrepancy. You can also take the limit as you can also look at the extreme case where you have a maximum number of resampling events. So this corresponds to the most amount of particle interaction. So it does monotonically decrease, but it doesn't go to zero by adding more resampling. So there is a certain like marginal gain that you have by resampling too often, but you still have this exponential dependency that you end up occurring, like in the best case scenario. Finally, you have so if you fix the number of resampling times and you fix n, and you now just look at the case, what happens as the discrepancy increases? So as the discrepancy goes to infinity, so as like my reference and target get farther and farther away from each other, or if I pick a bad schedule, a bad set of annealing distributions which do not share a lot of overlap, you're going to still get this exponential dependency. So notice over here, the resampling does make a difference. So resampling in the case where you have like a large discrepancy basically generates like in this asymptotic regime, n to the row number of particles. So effectively resampling is effectively creating more particles like fictitiously, which explains why resampling is a really meaningful thing to do. And it's a good thing to do when you have a bad path that you've chosen. However, notice how if this discrepancy goes to zero, as this D term goes to zero, you can do the Taylor expansion and the role of resampling disappears. And you end up, and also this exponential disappears. And you end up getting that the variance scales linearly with this discrepancy divided by the number of particles. So this kind of gives us an insight that the way to overcome this exponential barrier that's seen as like endemic to these important sampling-based algorithms corresponds to picking this discrepancy to be small. So what is this discrepancy? So the way that we can, so this incremental weight essentially corresponds to measuring how much change occurs from one distribution to the next. We can measure that through this normalized incremental weight, which basically in this particular case corresponds to the radon-Nikodym derivative between the reference from distribution one to the next distribution. So so remember, like the normalizing constant estimator is controlled by these incremental weights. So you can see already that the discrepancy from one distribution to the next should be controlled by the variance of these incremental weights. So the natural one that ends up arising is by looking at the log of the one plus the variance. So this is sometimes called the Rainey alpha divergence between this coincides with the Rainey 2 divergence between the reference and target from pi beta to pi beta prime, sorry. So this d of beta beta prime, this is now, we're pretending this is like a function that tells you like how much change occurs from distribution 1 to distribution 2. And when the two successive distributions are close to each other, this discrepancy is going to be low. And when the two distributions are going to be far away from each other, the discrepancy is going to be very high. This formula also generalizes to an arbitrary SMC sampler, not just this like likelihood ratio, but for the purpose of here, I'm just looking at this likelihood. So the total discrepancy, this DT term that I had earlier, you can basically it equals the cumulative discrepancy that we have along our annealing distributions. So if I have my sequence of annealing distributions, pi beta 0, pi beta 1, pi beta 2, all the way up to pi beta t, this dt corresponds to the discrepancy from these beta 0 to beta 1 to beta 2, et cetera, all the way up to beta t. So this has like the total discrepancy, it's like the total change in distribution that I've accumulated along the path. So what we want to now analyze is how do we make this thing small? Because like the reference and target, we don't have control over. The reference and target are fixed. And we have this pi beta that is like, that's the thing that we can interpolate. So maybe like by increasing the number of distributions, we have a mechanism of actually taking these discrepancies to be quite small. So like if I increase the number of distributions, I can ensure that the discrepancy from one distribution to the next is going to be closer and closer to each other. That's going to correspond to this, the change in our annealing parameter is going to get small. And hopefully we're going to always be within this low discrepancy regime. So in order to do this, we're effectively asking what happens when we take the increase in density of our annealing schedule itself. So when we take T to be quite large, this is the equivalent of analyzing what happens to the continuum of this path. So to analyze this a bit more concretely, I want to first take a step back and look at, forget about the discrete approximations that the discrete our discretization of our annealing path itself. And let's look at the annealing path as a continuous parameter, or as a continuous quantity. So if I have P of X is the space of probability densities supported on X, you can now reinterpret this annealing path that we had earlier as a curve in the space of probability distributions. And this beta parameter that we had, you can interpret this as a parameterization of this curve. So if I have distribution 1 and distribution 2, then so suppose I have beta and beta prime like on this path, then this incremental weight that we had earlier measures the change in position. So it tells us like how much change is occurring like in the density from one distribution to the next. We care about the change in terms of these densities because we are only really able to prod the annealing distributions through the weights themselves. So if I look at the instantaneous change of our position, this corresponds to a velocity. So in particular, if I take the incremental weight and I ask what happens as I make beta prime get closer and closer to beta, G beta beta prime is going to go to 1. So if I look at the derivative of this guy as a function of beta prime, and then I take the limit as beta prime equals beta, this is going to tell us, like, for a small perturbation in beta, how is the mass changing? There's going to be some regions where the mass is going to increase, some regions where the mass is going to decrease. And this is precisely what's encoded in by the Fisher score function. So this equals so this velocity effectively corresponds to the derivative of the log of the density. So when you're looking at this Fisher score, we all know that when you take an average of this Fisher score, there's going to be some regions where it's going to be high, some regions where it's going to be low, and the average is always going to be 0. So what we're really interested in quantifying is like the magnitude of the change. And this is going to correspond to maybe the standard deviation of the Fisher score. So if I have a magnitude of a velocity, this gives me a speed. We call this the local barrier because this, as we'll see later on why that's the name, but in some sense, you can interpret this like lambda of beta as how sensitive is our annealing distribution to small perturbations in beta. So this gives us like how rapidly our distribution is changing if I perturb beta by a small amount. So if I integrate the speed of a curve, that gives me a length. So this capital lambda, which I'm going to call the global barrier, is in some sense encodes like the length of our annealing path. And we're going to see that this encodes like the difficulty of our sampling problem and measures like how far away the reference and target are from each other and how it impacts the performance of our algorithm. So as an example of like what this like length looks like in practice, it turns out there are things that are necessarily hard for us or like necessarily high dimensional don't necessarily correspond to like a high length, at least as far as the Fisher, as far as this geometry is concerned. So this is like a variety of problems from physics and Bayesian inference. Some have data, some do not, of various dimensionalities, and you can kind of see what the different lengths look like. So larger lambda means that the reference and target are far away from each other. Smaller lambda means that they're not. So we now have effectively talked about 2 different ways of quantifying the change in our distribution. One that was related to the algorithm via these incremental discrepancies, and the other one related to the geometry. So you can ask what happens, like, are these quantities related to each other? And they should be, right? Because they both depend on these incremental discrepancies, these incremental weights. So if you do the Taylor expansion, you can show that this incremental discrepancy equals the local barrier squared. So it's like this incremental discrepancy is locally quadratic. And in particular, it's equal to the local barrier squared times the change in annealing parameter squared, plus some third order error terms. You can actually show if you pick the linear path from the reference target, this becomes a fourth order. So this becomes a really good approximation in practice. So in particular, if I have my number of distributions is sufficiently large enough where this geometry kicks in, then the square root of this incremental discrepancy from one distribution to the next is an approximation of the length accumulated from along my annealing path from beta t minus 1 to beta t. So the way we get this by taking square roots of this, if we take the square roots of both sides, basically the quadratics terms disappear, and this gives us an approximation of a Riemann sum. So by summing up the square roots of this discrepancy, we end up getting a pretty good approximation of the length. Notice how here, this was true independent of the choice of annealing parameters. All I required was t was sufficiently large enough for this to kick in. So in particular, for a fixed rho and for a fixed n, the thing that we really, the variance of our normalizing constant estimator corresponds to minimizing the sum of these discrepancies with this constraint that the sum of the square roots of these discrepancies is equal to lambda. I'm just pretending that this like approximately equal to is now an equal to sign. And you can do this optimization and you end up getting that the optimal annealing schedule satisfies the length accumulated from one distribution to the next is constant. So in particular, you want to pick the annealing parameters in such a way that it's reparameterizing our path of constant speed. So we're traversing their path with the same like speed. And in particular, when you pick this optimal schedule, the incremental discrepancy is going to be approximately constant, which is not that surprising. We want to, if we're basically thinking about these annealing distributions as like a ladder from one distribution to the next, we want to essentially have all the rungs of our ladder be roughly constant distance away from each other. So what does this look like in practice? So this is an example of an easing model where there's been, where you can show there's some phase transitions that occur. So uniform changes in beta do not necessarily correspond to uniform changes in the distribution, right? So in this particular case, you have that there's a critical phenomenon that occurs at roughly beta equals 0.4. So this is where the optimal schedule will correspond to putting in a higher number of distributions where there's rapid changes occurring and spacing them out further where there's a bit more stability. And we'll see later on that we don't actually need to know we don't need to actually do math to know where these like rapid changes are occurring. Our algorithm will figure that out for us. So assuming for now that we have an optimal schedule and we have n particles with row perfect resampling times, then we can plug in the approximation that we had earlier into our variance formula, and you end up getting it's approximately equal to 1 plus the exponential of this lambda squared divided by rho times t minus 1 over n to the power rho minus 1. So remember, n corresponds to our parallel cost. This is the number of particles. T corresponds to the number of distributions, which again is our sequential cost. And rho represents our optimally timed resampling events, which is in some sense our optimal communication cost. So under these assumptions, we can ask, how many particles do I actually need to get a stable variance related to lambda? So in particular, let's suppose epsilon is fixed, and I want to tune my algorithm in such a way that I want to ask how many particles do I need to get a variance within epsilon. So you can set this left-hand side equal to epsilon, pretend this equality, and then just kind of move things around. And you end up getting that n is approximately equal to this guy. So this is the number of particles that we need to get a stable estimate. So how does this actually like work in practice, right? Like how does this scale as the difficulty of the problem gets hard? So we can now take a new scaling limit. So this is like, instead of looking at the scaling with the computational resources, we can ask how does the performance of the SMC samplers change as the difficulty of the problem gets harder and harder? You can already imagine, right? Like as my reference and target get farther and farther away from each other, I'm going to need more distributions to interpolate between them. And in particular, I'm going to need to like most likely increase the number of distributions relative to the difficulty of my problem. And you can also imagine as my reference and target get farther and farther away from each other, I'm going to need my particles to interact more and more often. Again, proportional to the difficulty of the problem. So if I assume now that the number of distributions scales like lambda to the alpha t, and the number of interactions scale like lambda to the alpha rho. So alpha t measures the density of annealing path, like how densely am I populating my annealing distribution? So alpha t equals 1. When alpha t is less than 1, it's going to be sparse relative to the difficulty of the problem. When alpha t is much bigger than 1, it's going to be roughly dense. And then the alpha rho represents like the rate of particle interaction relative to the difficulty of the problem. So as alpha rho increases, we have particles interact more. As alpha rho decreases, they interact less. Remember, rho is always less than or equal to t, so alpha rho always has to be less than or equal to alpha t. So there turns out, like if you do the analysis, there are 3 distinct regions that end up forming. It's kind of like the equivalent of a phase diagram in like statistical mechanics. So when you don't have enough distributions relative to the length, and you don't have enough particle interaction. So in particular, when alpha t plus alpha rho is less than 2, you can show that you need at least an exponential number of particles in the length to get a variance within epsilon. But there's this magical thing that happens, like when you have enough density of annealing distributions, and you have enough particle interaction, that this drops down sharply from an exponential dependency to a sublinear. So alpha t in this case is less than or equal to 2, so this is a sublinear dependency. Notice how also when you enter this critical regime, you don't have the resampling stops mattering. So basically, like once you're in the stable regime, you just want to have enough particle interaction so that you're stable, but beyond that, you don't want anything more. Then there's this third regime that forms when you have the number of distributions grows quadratically. So when it's like the number of distributions grows on the order of lambda squared. In this particular case, you can show that regardless of the resampling strategy, you're going to need at most 1 particle. You can get a stable normalizing constant with just a single particle. So in some sense, like the sparse regime corresponds to importance sampling. Like this is where you have no annealing distributions whatsoever, and it explains why importance sampling sucks. But then once you have enough distributions to achieve this stability, you end up dropping from this exponential dependency to a sublinear, which explains why SMC samplers is state-of-the-art. And this is more endemic to annealing algorithms more broadly, but we'll talk about that a bit later on. So we now have these 3 different regimes. So let's ask what does our different resampling strategies look like? So annealed importance sampling, remember, this is the case where I have no resampling. So the number of resampling moves that I have does not scale with the number of distributions or the difficulty of the problem. So in this particular case, alpha rho is always equal to 0. So annealed importance sampling, effectively, in order to achieve stability, you need to have the number of distributions to be on the order of lambda squared. But once you have achieved that stability, you are super efficient. You can get a stable normalizing constant estimator with a single particle, and you don't need to have any interaction with curve whatsoever. The other extreme is the case where I am resampling every iteration. So in this case, I'm effectively triggering a resampling event proportional to the number of distributions that I have. So alpha t is equal to alpha rho. And in this case, to achieve stability, this requires meeting this threshold where alpha t is equal to 1. So in this case, the number of distributions that you need to get stability with frequent resampling is on the order of lambda. But the penalty you pay for that is you also need to have your particles interact. And that means you need to have the number of particles be on the order of lambda, and also the number of interactions be on the order of lambda. So it's not one is better than the other, so they're reshifting their compute resources. So your AIS requires more runtime, but fewer interactions and particles, whereas sequential importance sampling requires less runtime to achieve stability, but requires, again, more interaction. The third regime is adaptive resampling. This is probably the most commonly used one. And notice how this is actually slightly more interesting. So to achieve stability, it still requires a t on the order of lambda distributions. But once you've achieved that, like notice how adaptive resampling you can show hugs this stable curve. So adaptive resampling behaves like sequential importance sampling when you have a coarse schedule, and it behaves like annealed importance sampling when you have a very dense schedule. And in the middle, it will trigger a resampling event only when it's required with the right proportionality. So this explains why adaptive resampling works really well out of the box, and it kind of like scales the number of resampling events proportional to the difficulty of the problem naturally, as well as the density of the schedule. So we now know how many distributions we need. We know how to pick our schedule, like what the optimal schedule looks like. We have our resampling strategy. How do we actually get this schedule itself? Like this is kind of where, in practice, what you actually want to be able to do without needing to like think very hard or do math. So the schedule turns out to be the algorithm turns out to be quite simple. You can actually approximate this incremental discrepancy using the incremental weights that you've already been running your algorithm. So you run SMC sampler with some schedule of size TR and some number of particles NR. You get an approximation of the discrepancies. You can then look at the sum of the square roots and like basically look at this cumulative sum, which again, this is a very simple thing to do. You can then do a one-dimensional spline interpolation. And this gives you a continuous parameter. And then now you just do a one-dimensional inverse transform to get what an optimal schedule looks like. So remember, the optimal schedule accumulates the same amount of length at every iteration. So essentially, we want to chop up the y-axis into t intervals, and then look at what is the annealing parameter that corresponds to it. And this will give us a new schedule. And again, we can query a new increase the number of distributions if we want. And we can plug that into a new SMC sampler, maybe run it for twice as many distributions or more particles. And then you can repeat the process. So each circle here corresponds to a round. So the idea here is that every round, we're going to double the cost. So we're effectively using the previous round that's cheap to precondition on where the best annealing distribution should be for the next round. And we can repeat that over and over again until we've depleted, until either we've achieved stability or we have depleted our tuning budget. So this is what the schedule kind of looks like, or this is what the behavior kind of looks like as you increase the number of rounds. So notice how initially it's kind of all over the place, then it starts to like stabilize. This is an example of what the local barrier looks like as a function of the rounds. And you can kind of see like it will kind of figure out where the rapid changes are occurring without you needing to like hand tune anything. So this is a very black box. In comparison to what people have been doing in practice, traditionally what people have been doing is an online schedule tuning. So the idea here that is you take your particle approximation at time t, or t minus 1, and then you use that to estimate what the next one will be. Typically, that's done via a line search. So you compute this thing called a conditional ESS. I'm not going into the details of what it is, but again, it's a quantity that you can approximate. And you have some specified threshold delta, where you are doing a line search until you figure out what is the next annealing distribution that will get me a conditional ESS of delta, and then you repeat that over and over again. This has some issues where the first one is that there's a hyperparameter you have to tune, i.e. delta. It's also an online algorithm, so like you have to do this sequentially. You also lose some unbiasedness because you are peeking ahead of what the next distribution is. So you don't necessarily preserve the unbiasedness of the normalizing constant estimator naively. And in particular, it's also like a random runtime, right? Because you don't know how long it's going to take for it to terminate. So what ends up happening is that with SMC sampler, it's only useful until you terminate. So if you have maybe if you chose a delta to be bad, and you've depleted your budget before you finish, you might not get a useful result at all. So this round-based approach circumvents this altogether. And it turns out it's also equivalent to the online procedure that we had earlier. That's been used canonically in the literature. So this conditional ESS quantity that you can compute using the incremental weights, this turns out to actually be in log scale an approximation of this d hat parameter that we had earlier. So this, by getting a constant conditional ESS, this actually gives you a constant incremental discrepancy as well. Because we have pre-specified what the number of distributions are in every single round, it's deterministic runtime. We know each round how long it will take to terminate, and we can cut it off at an earlier round if we lose our budget altogether. There's also no hyperparameters to tune with this like round-based approach, and you still preserve the unbiased estimates of the normalizing constants because of the fact that, again, you're using the previous round to estimate the next, to predict what the next schedule should be, rather than the current schedule to figure out the next schedule. This also allows us to the real benefits also come from allowing us to scale for annealed importance sampling. So AIS is far more memory efficient, and it's scalable to GPUs because we don't have to do a line search or any particle interaction. So you can show, like you can see, like when you're operating on a CPU, the advantages of doing this online procedure versus this round-based turns out to not be very different. But when you add this GPU, when you put into a GPU context, then we get some pretty substantial gains. So the blue is our method, the yellow is the online procedure. This adaptive resampling procedure as well allows us to actually see which regime that we're in. So when you have, remember, this adaptive procedure, like it triggers resampling events proportional, scales it with the number of distributions that you have. So if you have, in the earlier rounds, when you have like a fewer number of distributions, you're going to see this like relative ESS is going to be kind of all over the place. This indicates that you're triggering a resampling event every iteration. Once you've entered stability, you end up seeing this sawtooth pattern. So we're triggering a resampling event after the ESS drops below 50%. So, and then once you have enough distributions, you're never going to trigger a resampling event. So you can actually like see exactly which regime that you're in. So this isn't just like a theoretical tool. This is actually empirically valuable as well. These spherical Cow assumptions that we had earlier turns out to also be quite robust. So you can show that so this is where we are choosing how good we're making our MCMC move. And in particular, when you have very like small number of exploration steps in between, the dependencies become quite large, but you still see that we end up recovering good estimates of this local and global barrier. For the last 5 minutes, if I have time, I want to just like talk quickly about the competitor to SMC sampler that like as a practitioner, you have to decide which to use or not. So instead of doing this like SMC-based approach, you can also do an MCMC-based approach. So there's this algorithm called parallel tempering, which instead of generating all of our particles of the reference and the next distribution all at one at a time, we can do this all in parallel. So parallel tempering corresponds to generating n particles, each of them targeting a specific annealing distribution. And then we are going to update each of them in parallel according to an MCMC move targeting their respective annealing distribution. Then we do a communication step where we allow them to swap with each other via metropolis correction. So essentially, instead of using importance sampling as a way of keeping correctness, we're using metropolis Hastings. Then you can repeat this over and over again until you get a particle approximation across all the different distributions. In practice, what you want to do is not every iteration. You want to actually do this deterministic odd-even swap, but this is this non-reversible communication that leads to stability when you have a large number of distributions as well. This has been applied in a variety of contexts, and this is also competitive right now with the state-of-the-art of SMC samplers. So to ask when should you use one versus the other, so I want to just circle back to there is this computational duality that kind of occurs when you're looking at SMC-based methods versus MCMC-based methods. So if you look at SMC samplers where you're triggering and resampling every iteration, you're effectively generating n particles in parallel, and then the numbered annealing distributions corresponds to your sequential cost. So the particles are your parallel costs, the distributions are sequential. With parallel tempering, it kind of goes the opposite, where you have the number of distributions corresponds to your sequential cost. So the number of particles corresponds to your sequential cost, and the number of distributions corresponds to your parallel cost. In both cases, you end up recovering an estimate of the expectation by averaging out across the particle trajectory of the empirical distributions you have for your target. And you end up recovering estimates of the normalizing constant by averaging out across the particles approximations of the annealing distributions. And notice how the formulas are basically the same, where you're swapping the n and the t. So this computational duality also allows us to take our analysis that we just talked about for SMC samplers and apply it directly to parallel tempering. And so you see that there's this asymmetry that occurs between the number of particles and the number of distributions. So in particular, when you don't have enough distributions for stability, both algorithms fall apart. So you basically want to have enough distributions where you have achieved the stable regime. But then once you have that, you really gain advantage, not by adding more distributions, but by cranking up the number of particles. So which algorithm you should use in practice actually boils down to your computational budget and constraints rather than one algorithm is better than the other. So in particular, if you're rich in time and not poor in parallelism, then you should use parallel tempering, because this means that the time, remember, corresponds to how many particles that you have, and you need to have enough parallel distributions in order to achieve stability. If you're rich in parallelism, but not poor in time, then SMC samplers turns out to be the right thing to do. If you're rich in both parallelism and time, it turns out doesn't matter. At least for normalizing constants, they're both going to give you the same results. So pick whichever one is algorithmically easier to implement. And if you're poor in both, then that means you have to start getting a bit more creative and start thinking about how you can incorporate flexibility in these neural-based methods. And in practice, what you end up seeing is all of these different methods, and for normalizing constants, perform the same. So this is for the zoo of problems that we applied it on with parallel tempering, as well as this annealed importance sampling, as well as SMC samplers. When you normalize the number of exploration steps, the number of MCMC moves or function evaluations, they will all give you roughly the same amount of same estimates roughly over time. Yeah, thank you. I think I may have gone a bit over time, but